Thank you for the introduction. I would just like to say a few words about our research that regards the behavior of fiber-reinforced plastics in marine environment. Sorry. I will take you to the, let's say, regular steps that we usually do it. How this all started. Roughly 5 years ago, there was an article in local media and some kind of media exposure of the two of the biggest shipyards in Croatia that boasted a bit about some, let's say, advancements that they have made in ship construction. And they constructed basically two ferries, car ferries, with the entire superstructure of the ship being made in composite materials. And what they have achieved is this kind of, let's say, advancements or betterment of the ship itself, reducing fuel consumption, and with the reducement of the mass of the ship, increasing the carrying capacity of the ship. These two factors basically, I don't know if some of you here are from the shipbuilding industry or any kind of maritime sector, but these two factors constitute something that is called energy efficiency evaluation index. With all of these great things they have achieved, they also they posed some question, why didn't we do this sooner, okay? And they concluded that the shipbuilding industry is very traditional and very unwilling to accept changes in any kind of regulations. Why is this point in red? Because I want you to remind you that all the regulations in the shipbuilding industry come from insurance companies. Okay, so basically money is very important here, and therefore there is the unwillingness to change. And they requested basically for simple engineering tools that can be used in their process of designing of the ship and any other maritime structure. So the big idea for us was to find out on a more, let's say, scientific level, what does the sea, the real sea environment, do to such materials when they are exposed to the sea. Of course, step number 0 in any research is to find money. So we basically tried to do this and manage it to do it, and find some reliable partners and proceeded with the research. So our first idea was to keep everything on a macro-meso level of analysis. Because of that request for simple engineering tools, we decided to use coupons made of epoxy and polyester resins reinforced with continuous glass fibers. Why that? Because that was the choice of the people from the shipyard, main choice that would try to make when they decide to build composite ships. Chose some very, let's say, regularly applied fiber layout configurations in, generally speaking, in composite structures, according to standards, applicable standards, and decided to use end tabs to minimize the influence of the equipment used for testing. And the coupon looked like this when we finished it. The next step was obviously manufacturing the coupons. They were cutouts out from 30 by 40 centimeter plates, produced by vacuum-assisted infusion for epoxy coupons and hand layup for polyester coupons. We opted for water jet cutting for one, let's say, simple reason, because we had some previous experience with water jet cutting, and with brittle materials such as this kind of plastic you can induce specific damage points, but just choosing where the cutting flow will start. So you will have like a little bit breakage here. Why? We wanted to have a simulation of a damage spot on a ship, on a hull or anything, and see whether this existence of any kind of damage on the structure will have any behavior of it on its behavior, on its any influence on its behavior. Then we designed by ourselves and manufactured by ourselves a submersion assembly that looked like this when finished. In total, 6 of them, some 100 coupons were submerged into the water. in various combinations of materials and fiber orientations. The submersions were done in front of the Rijeka Bay in Croatia for a period of 6, 12, and 24 months. And I would like to emphasize here in real time, not accelerated tests, and in real environment. Whatever the sea decided to do, we accepted it. We didn't want to do anything, let's say, too laboratory concentrated. Of course, you have to find a team member that can dive, ask him to do so, wait, then bother him again to take out all the coupons outside. And immediately, this is the coupon set that was under the sea for 6 months. You can see various attachments of marine organisms on it. And that's the main difference between laboratory tests and real environment tests, because you don't have this kind of organisms in the laboratory test. After that, we try to identify whether are any changes in the mass of the coupons due to biological growth of this attachment, all of these kinds of organisms, and water absorption, obviously as expected. As the coupons were longer under the sea, this mass gain was bigger. After that, we cleaned the coupons carefully and evaluated just the absorption of the seawater in the coupons. As you can see, for the epoxy coupons, there is some of the configurations did not exhibit saturation characteristics, whilst polyester, the resin polyester, all of the coupons basically were already saturated after 1 year in the sea. The next step was to identify the basic material parameters. A tensile test was done on a universal testing machine, and basically we got all kind of types of failure in the coupons. These are some typical stress-strain curves showing, let's say, some variations in elasticity, but the obvious reduction in characteristic was the loss of ultimate tensile strength. Why did we did all of this? To be able to model SN curves based on the ultimate tensile strength. I left this curve here, but I was trying to decide whether to incorporate this curve or not in the presentation, and I decided to do so just to remind everybody what's the main difference between composite material and steel. This, let's say, deviation from the behavior was due to only one coupon, which had a significantly larger number of glass fibers inside the coupon. It was basically a manufacturing error. If you know that the glass has a very high tensile strength, so if I removed this one coupon, the curve would be very similar to the other ones, no? So basically, just to remind everybody of the importance of manufacturing in composite materials. We did some microscopy analysis, but I don't want to bother you here because they have already been published. There is a huge repository of these scanning electron microscope images on the internet, so you can go and check it out. What can I say? You can see a lot of various types of organisms either attached or embedded into the resin itself. And I will tell you later why this is important. All the information, what we wanted to finally achieve is to be able to make a correction in the SN curve of the, let's say, theoretical SN curve, just to be able to simulate, or not simulate, but try to guess what would be the fatigue life of the composite material itself. What other authors and regulations, let's say, recommend is to use this kind of model for failure model analysis. With this, alpha and beta coefficients are typical or can be achieved for a specific combination of resin and fiber layout configurations. And after we gathered all the data, we did some regression analysis. Why do I say here polyester, I don't mention epoxy anymore, because somebody stole one of the assemblies that were submerged, and unfortunately we don't have results for epoxy resin. But if we, let's say, try to construct a prediction for all these blue dots are the data, not all the data, but just the maximum and minimum for each time period that we considered, we can obtain some simple mathematical formula that can illustrate the loss or the prediction of loss of ultimate tensile strength. I will say immediately that I myself am not very satisfied with this because of the relatively small number of measurements or coupons on 100 in total. It would be better if we had some more results. And if we combine all of the two equations before, we can obtain a simple, relatively simple equation that can be used to predict for longer periods the fatigue life of the composite itself when exposed to real emphasis on real marine environment. And it basically, you can see all the fiber layout configurations exhibit very similar behavior. If we normalize all of that, by normalizing I mean I choose a single value for material parameters alpha and beta, then for different fiber layout configurations and percentage of ultimate tensile strength that the real construction or the structure has to endure, we can have these predictions of fatigue life expectancy decrease in exploitation. So what can we conclude from this really a small part of our research results? That the real sea environment has considerable effect on composite materials that have to be taken into account, not just the idealized artificial seawater and climate chambers into the laboratories. This is manifested by increasing the mass by biogrowth, embedding salt crystals and water itself. Then the mechanical strength is reduced. And what from all the other images that you can find on the web, on the repository with the published articles, basically all of these organisms created something that, to retain the terminology from composite materials, can be called voids. So whether these organisms eat the resin on drill, I have two biologists that are still arguing about that. Nobody can tell me what's happening for real. So fatigue life decrease can be expected, and it's all can be evaluated, this initial model, only by based on the ultimate tensile strength of dry coupons, which brings me back to the simple engineering tool, okay? Because if you go to the shipyard and say you need to do some microanalysis, they will tell you no thank you. So all of this mathematical model was based on experimental data and basically point to the need of correct the fatigue life predicting procedures prescribed by the aforementioned societies. And also the importance of this biofouling is also noticeable. For further research, I would like more results and to, let's say, refine all the curves that I've shown you. Before I thank you for my attention, I would like to extend and join to the invitation of Professor Božić for the conference that will be held in Dubrovnik later this year. So please contact him for any further question. And now I can thank you for the attention.
Thank you for the nice presentation. Thank you.